So let's take some questions from the homeworks. Okay, so Ava, I know that you had already mentioned this, so we'll start with you. Amanda, I see you though, you're going next. Where are we at here?
47.
47. Okay. Make sure I have that open so I can see that. All right, let's see here. I'm just going to read these aloud. I'm not going to write the words down. I hope that's okay with everybody. So a crate of negligible weight is being pulled up a ramp at an angle of elevation of 38 degrees. Oh, thank you. We're trying here, guys. We're trying. Oh, good. So here's like my ramp, and there's my angle of elevation of 38 degrees. Oh, I'm sorry, the ramp has an angle of elevation of 25 degrees. Sorry, I didn't read that very well. It's a little poorly worded in my opinion, but who knows? I helped write the book. It says a crate of negligible weight is being pulled up the ramp at an angle of 38 degrees with a force of 120. So like, let's make this our crate vector. So that's 38 degrees. We know the magnitude is 120 pounds. And it says, what is the amount of force being directed up the ramp? So what we're looking for is the projection of C onto R. So to do that, what do? We do C dot R divided by the magnitude of R squared times the vector R. And then we're going to want the magnitude of that vector. Will be our answer, whatever that is. So we have to resolve C and R into component form. So C, it's pretty clear what to do there. So it's just going to be 120 cosine 38 plus 120 sine 38. And then R, we're not told any information about how long this ramp is. So we're free to assume that R has magnitude 1. So R is just going to be cosine 25 comma sine 25. So that's my vectors C and R. And I'm going to plug those into my formula here. So I'm going to have 120 cosine 38 times cosine 25 plus 120 sine 38 times sine 25 all over 1 times that vector cosine 25 comma sine 25. So fire our calculator here. Do I still have mine open? Oh, I do. Or I don't. Either way. So I'm going to have 120 cosine 38 times cosine 25 times cosine 25. So that's 77.67. And then the same thing, except I have sines now. 38 sine 25 sine 25. 40s. Oops. Can't read that if I don't have it. Let me just double check to make sure what mode I'm in. Okay. Don't want to get too far if I'm in the wrong mode, you know. So 77.67 comma 113.20. That all looks correct so far, right? You guys, I didn't goof up. Yeah.
Can you get the dot product before you stand by the other?
Yeah. Yeah. If you want to do it in like 2 steps, that's no problem. Oh my goodness. Yeah. Oh boy, I goofed that up really bad, didn't I? Jeepers creepers, Mr. Kulik. Yes, thank you. I see what you're saying, Keaton. Yes, thank you. So I have this. Plus this. I didn't finish the dot product before I started distributing, and I goofed it all the heck up. So I have that, it's the dot product, and then that is times cosine 25. Thank you. That looks better. 113.89 is my first component. Ava, did you see what I did there differently?
Yes.
Okay. And I don't know, Amanda, if you're interested in the same question or not, but I almost made a very bad boo-boo. And then 53.11. Okay. That's better. Thank you, Keaton, again, for catching that. I would have been sitting there staring at that for a long time wondering, what the heck did I do wrong? So, and that gives me about an impossible answer. Well, that's not cool. Why is that an impossible answer? So just think about it from a practical standpoint. We're pulling with a force of 120 pounds, and somehow that's directing more than the amount of force we're pulling. That's kind of violates some fundamental laws of physics, right, where we have conservation of energies. So I goofed something up when I typed these into my calculator. I did too much at one time. Let's try this again. All right, so 120 cosine 38 times cosine 25, and then plus 120 sine 38 times sine 25, 16. I'll multiply that by cosine 25. That's 105. That would do it. This is why I get punished for trying to do too much on my calculator all at once. In fairness, the calculator I like to use has a much better display than this crappy thing does. I hate that it doesn't wrap, you know? And then I'll take that and multiply it by sine 25. That's 49.41. And then if we do the Pythagorean theorem on that, that seems like we got a little bit better odds of coming out with something that's not impossible, right? There we go. That seems better. Is that the answer I'm supposed to get? It is. Okay. So just from a physics standpoint, if you think about this, you're pulling at 38 degrees relative to a ramp of 25 degrees. You're almost pulling in this exactly parallel to the ramp, right? If you're exactly parallel to the ramp and it's frictionless, it should be at the same, your force should be equal. You're just a little bit off, so you're wasting a little bit of energy. You have almost 120 pounds still pulling. So that to me is an answer that makes sense. If your answer is bigger than 120, you know something is goofed up. Like as soon as I wrote that answer down, I'm like, well, that's not right. Or if it's way less than 120, that would be a bad sign too. It should be pretty close, since the difference of those two angles is pretty similar. Keaton.
On a test, when you have to go through all that, they just give it out.
If you wrote down like, if you wrote down like how you got these things, like I don't need to see all the work written down on the sheet of paper.
Yeah, but
Oh, you're saying that, I see what you're saying. That this number was the same as this number. That's what you're saying. Okay. Let me think about that. Is that going to happen all the time?
it said on the lesson every time that bottom factor is 1.
Gotcha. Oh, and that, of course, that's going to make sense. Why is that got to be true? Let's think about that. So here's why that's got to be true. So if I do just the norm, or the, I want to keep calling it that because that's what we call it in math class, but we're doing physics class kind of right now. Well, I guess it's still physics, but it's the more general statement is calling those magnitudes norms, but beyond the scope of this. So if I do this, this is just a scalar, right? That scalar can just get pulled right out front. Since the absolute value of that scalar is just itself. So really it's going to be that scalar times the magnitude of that vector. And what's that magnitude? 1. So that's why that's going to work. So yes, you're right, Keaton. You could take that shortcut. Yep. Yeah, no problem. That's a good question. A nice one to point out. Sophia? Yes. I'm going to hit up Amanda here because she was trying to ask a question right away too, but we'll certainly come back and do 35 if she does not. If she has a question or if it's a question not related to 35.
Did you do
49. Yep. And Sophia, you're on deck, okay? Okay. I'm just trying to communicate, right? Like I'm not trying to play favorites or whatever, just trying to go in order. All right. A crate is being pulled a ramp at an angle of elevation of 48 degrees with a force, 50-pound crate is being pulled up a ramp at an angle of elevation of 48 degrees with a force of 150 pounds. The ramp has an angle of elevation. What is the amount of force being directed up the ramp? Okay, so I read this and I hear 3 vectors. Do you guys agree with the same thing? You have a gravity vector, you have your pulling vector, and then you have your ramp vector. In real quick. See, the ramp is 30, and we're not told any information about that. So that's what the ramp vector is going to look like. Then we have the crate vector. We're told the magnitude of that is, maybe I should call that, I'm going to still call it C, is 150. So that is 150 cosine of 48. And then we have our gravity vector. So that's 0, -50. Oops. Made a little typo there when I wrote that down on my crate vector. There should be a 150 in front of that sign there. You guys probably wrote it. I just forgot to. Okay. What we want to do here, because this is a little bit different. My suspicion is that what we're going to want to do is we're going to want to project the vector ramp R. That's my suspicion. Let's check that and make sure that we get the right answer, but that's what my gut would tell me to do. Since C plus G would be the net force acting on the ramp. Keaton, are you going to tell me I'm doing it wrong? So it says the crate weighs 50 pounds. So weight is just a function of gravity. Gravity pulls straight down. So that's where that came from. Is that okay?
Yeah.
Okay. All right. So let's do C plus G first, since there's probably no good reason to be obtuse about that. So where's my calculator? I keep looking for something that's not there. So 150 cosine 48 plus 0 is just going to be 100.37, and then 150 sine 48 plus -50, or just subtract 50, is 61.47. So I'm going to write those numbers down. Uh, 100 point, and then 60. And then, according to what we just learned in the previous one, is that, so we have this x component times cosine 35, that's the x component for r, plus the y component times 35. That's the y component for r. And that gives me 117.48, which is what I was supposed to get. Oh, good. Because if it wasn't supposed to be done that way, I was like, now I'm really at a loss for what I would want to do. Keaton.
Why do we have to stand for approximately?
Well, I rounded,
Oh,
right? Like there's more decimals there. I just rounded to 2 decimal places is why I said approximately. That's all. I just have gotten in the habit, like some people are, I've been in classes where people are very picky about a rounded answer with an equal sign versus a rounded answer with an approximate, and I have been beat into me that if I round, I write an approximate versus a hard equal sign is only if it's like truly equal. That's all. I'm not going to care that much for you. I think on the IB test they care that much, though. Yeah. Amanda, are you happy?
Yeah.
Yeah. Thinking to add the 2 vectors that are acting on the ramp is the key there. If you didn't think to do that, it's maybe not so clear. Like, do I just do one projection, then another projection onto it? I'm like, the second thing I tried, I'm not sure. It seems much harder than just adding them and then doing it. No problem. And look at something from last time, right?
Yeah.
35, okay. We can do that. I see you still writing. Do you need a minute? It's okay to say yes.
Yeah.
Yeah. No problem. I get it. That's why we do them in class, right? So you guys can write them down and come back and look at them. And again, I go fast sometimes, so if I'm going too fast and you need a minute, well, what we're doing is down for a minute so you can catch up. Okay, so we want V. So if I go back and I look at the formula, we had a formula for this. Where was it? Just want to double check because I don't want to write down the wrong thing. I think I remember what it is, but knowing my luck, I would have written down the wrong thing, and I don't want to do that too. So that's the formula. So that's all I'm going to use. So I'm going to just start out by calculating the dot product and then the two magnitudes. And then I'll just plug those into the formulas. So that's negative 12 plus negative 40, so that's negative 52. So that's 9 plus 64, that's 73, the square root. So 16 plus 35 is 41. Inverse of negative 52 over square root 73 times square root 41. So far, so good. So, okay. And then we'll just type this into our calculator. I like to do this all in one line because I'm going to use the fraction command. If you don't know how to do that, if you press alpha and then the y equals button and pick the first option, it gives you like a fraction into your calculator. So you can't screw up the parentheses or whatever on the fraction. Sometimes it's easy to do that if you're going quick. This is nice because it's going to show you exactly what it looks like. So you'll know, like, looking at your calculator, like, oh, buggers, I've typed something in wrong, because it doesn't look exactly like your sheet of paper does. So I do that, I get 161 and 0.90, I guess. Does that feel okay there, Sophers? Okay. So again, just basically using the formulas, right? So not so bad. Okay. Anybody else here with questions from the homeworks or in general? You know, happy to do more if you still got more. I know, Ava, you said you had 2 questions. Did we get both of them?
49 was the one I was going to ask as well.
Perfect. Anthony? Sure. So it says, show that the following pair of vectors are orthogonal to each other. Just to remind ourselves, orthogonal means that they meet at a 90-degree angle. And we have a theorem that we'll use to kind of do this proof. So we know that U and V are orthogonal if and only if U dot V is equal to 1, or I'm sorry, 0. Okay. And the reason that is because I know that cos 0 is equal to 90 degrees.
Yeah.
So the only way that angle between the two vectors formula is going to spit out 90 degrees is if the numerator is 0, which is their dot product. So we can simplify that all the way down just to looking at their dot product. So u dot v is going to be 8 times -3 plus -1/2 times -48. So -24 is 0, and we're done. That's it. Yeah. So again, all we have to do is show the dot product is 0. And while the dot product is like a new operation, it's a pretty easy operation to do, where we just multiply the coordinates and add them together. Yeah, no problem. All right. So let's do a little bit forward into section 4. Not much, though. I don't know. We'll see what we do. But you guys are good with questions here? I think we did a good variety of stuff, right? Should be quite a bit to kind of get you going forward on things. So first thing we'll do in this section is we're going to introduce another notation for a vector. I guess we refer to this as IB component form. In my math classes, we would have called this a column vector because it's written as a column rather than as a row. It's exactly the same thing as the component form. It has the same definition, it's just written as a column rather than a row. And we're using a parenthesis rather than a wedge. Like, what did he do, right? No big deal. The advantage here of writing your vector in this way is it's easier to tell the difference between a vector and a point at a glance, right? So we're going to start talking about vector equations for lines. So points are going to be involved. Can get a little confusing if your vectors are written as a row and your points are a row. So we're going to use this other notation to help differentiate between a vector and a point. Everybody's good with that? That rationale anyways? Okay. So remember back in your Algebra 1 class, when we want to find the equation for a line, we could do, if we had 2 points, or the slope and 1 point. Right? Those were kind of the two different situations we dealt with. The same is going to be kind of true here. Okay. So let's just kind of look at an example about, let's give us an equation for a line and translate it into the vector form and kind of explain how that works. And then we can start generalizing out from there. So we'll look at a specific example here. So maybe the line y equals 1/2 x plus 1. So you can find any point on this line. For this example, I'm going to choose the point 2, 2. Since I didn't want to pick something that had a 0, and I wanted to pick something that had a whole number, so that seemed like a good one. And I'm going to call this point P0. Again, the point that I'm picking here, though, is pretty arbitrary. I just picked something so that when we do the arithmetic, it's not trivial. Now, to describe this line, we need this point, and then we need a direction vector in the same direction as this line, right? Everybody's okay with that idea? So to describe this line using a vector, if you know a point and you know the direction, if you can start that vector at the same direction, starting at that point, and then extend all the way, you have the line. That's going to capture the same information, right? Like if we have just the direction, we don't know, we just have a vector parallel to that line. We need a point on the line to kind of fix the vector onto that specific line. You guys get what I mean? So any point on the line is going to be good for a location. To get the direction vector, what we'll use is the slope. So if our direction vector is, or if our slope is 1 over 2, our direction vector is just going to be 2 over 1. Why did it flip like that? Think about the definition of slope. Is change in y over change in x. So the y-coordinate is the numerator of the slope, and the x-coordinate is the denominator. So when we make our direction vector, the x component is the top and the y component is the bottom. So no big deal. It'll always be a reciprocal like that. If the slope was negative, would it matter which component we made negative? What do you guys think? No, it won't matter. Okay. So then we can say, okay, so I can take my equation and write this as P naught plus our vector, our direction vector. But this is a problem, right? Just from a notational standpoint. Because the sum here that we're being asked to do is with a point, an ordered pair, with a vector. Can we add those two things together? Does that make sense? No, not really, right? So what are we going to do? We're going to make the point a vector. Okay. Now, the issue is that vector v is like a set value. Right? So we can't really like extend this or whatever. So what we'll do is we'll just tack a scalar onto that direction vector. So if t is positive, you're getting 1/2 of the line starting at that point. And if t is the opposite sign, you get the other half of the line starting at that point p. So in general then, the way we write this is this, where r naught is our initial point, v is our direction vector, and r is our, should be a t on that, vector equation for the line. Okay. So for example, if we wanted to do this and write y equals 3x plus 5 as a vector equation, we're going to need a point on that line. What's an easy point on that line to get? About the y-intercept, right? We can get that just by looking at the thing. And our slope is 3 over 1, right? Now, did it matter which point I picked? Does not. Can my answers vary because of this? Yes. So that's okay. So I'll start by converting that point into a vector, and then I'm going to convert that slope into a vector. So my vector equation is just that. Keep in mind that if you picked a different point, 1 or 0, 5 could be something different, like what? 1, 8 is another point on that line. So you could have had 1, 8, but the direction vector should stay the same. Or at least be a scalar multiple of the direction vector. Like if you wrote the direction vector as 2, 6, that would still be okay.
Mr. Kulik,
Yes, sir.
just to check, are these supposed to be fractions or is there supposed to be no line?
They are not supposed to be fractions.
Okay, I just want to make sure.
Yep, those are column vectors, so they are not fractions. Good question. Okay. So what if we wanted to go the other direction? What if we started with a vector equation and wanted to turn that into a intercept? Well, that's the point, 3, negative 1. This is the slope, 3 over 2. So we can do negative 1 equals 3 over 2 times 3 plus b. And that gives me negative 11 over 2 is b. So we have y equals 3 over 2x minus 11 over 2. Sound okay to you? That should look very much like a Algebra 1 problem, right? All you had to do was translate to get the point and the slope out of there, but after that it's pretty easy. One more example problem will be done. Let's say we want to find the intersection of these two lines. Okay, so we want to find the intersection of these two lines. Well, one way you could do it would be to convert both of them back into slope-intercept form and use, like our Algebra 1 methods to find the intersection, but that's not very interesting, so let's do it using vectors. So the idea here is we want to find some vector xy that's on R1 and on R2. So if I do the vector addition on the right-hand side here, maybe I'll write that as a separate line. That probably makes more sense because I'm going to do another one after that. So that's going to give me 2 plus 1s plus 4 or over, and then 4 plus 3s, which basically turns into the system x equals 2 plus 1s, y equals 4 plus 3s. And then similarly, that same xy has to be on R2. So we can get the same thing, that x is going to be -1 plus 3t, and y is going to be 5 plus 5t. And now we can solve these as two systems where we take the parts that are equal to x and the parts that are equal to y together. So you guys see what I did there? So I set those x's equal to each other to get this equation. Similarly, I set these y's equal to each other to get this equation. And now we can just rearrange this to get it into a good form to solve. So subtract the 3t to one side and then subtract the 2 to the other side to get the variables all lined up. So there's my system. What's going to be the easiest way to solve this system? I'm going to solve it in my calculator using row reduced echelon form with a matrix, because I don't have to do any algebra to do that. You can solve them by hand if you prefer, but good lordy, this is so much faster and easier. Do you guys remember doing this in Algebra 3-4? Okay, well let's show you how to do this real quick then. That's okay.
I'm trying to figure out where it is.
That's okay. Are we okay with how I got to this system here? So I subtracted the 2 over and then subtracted the 3t over just to get everything lined up. Subtract the 2 and then subtract the 3t. Right? And then I did the same thing over here. Subtract the 4 over, subtract the 5t over. I'm just rearranging. Yeah. That's all. I didn't do any solving. So the idea here is I'm going to turn that system into this matrix. So I'm just going to take the coefficients from the system that I had before. Okay, everybody see the coefficient matrix? So it's just the coefficients. They have to line up, like the S's have to line up, the T's have to line up, the solution has to line up. And then we're going to do the command RREF on our calculator. And that's going to spit us out the result. So to enter this matrix into our calculator, we press second and then the matrix button. We go over to the Edit tab, pick one of the matrices that we want to check, or that we want to type this into. Set the dimensions. This has 2 rows and 3 columns, so it's a 2 by 3. And then I just type in the coefficients exactly as they look like on my sheet of paper there. Once I've done that, I'm going to exit out to the main screen, and I'm going to wait for you guys that are following along to kind of catch up. Okay. To get the RREF command, I'm going to go back to the matrix menu, but this time I'm going to go to the Math tab, and I'm going to scroll all the way down to the bottom till I see the RREF. It's like Command B. And I'm going to press Enter. That's going to paste it onto the home screen. And then I'm going to go back and retrieve that typed everything into, Matrix A, and press Enter. Now this matrix that I have tells me my answers for S and T. So this says 1S plus 0T is equal to 4.5, i.e. just S of 4.5. And then 0S plus 1T is equal to 2.5, i.e. T is equal to 2.5. So then to get my value for X or Y, I know X is equal to 2 plus 1S. So 2 plus 1 times 4.5. Just looking at this problem, and they in the book, and they made a typo. I was like, wait, that's not the right number. And then I can do the same thing with the Y. Again, doesn't matter which one I choose. I'm going to use the S one also. So that's 4 plus 3 times 4.5. So what is that? It's 12, 13 and a half, 17 and a half or something. Okay. So my point of intersection is this, or if we want to write it as a vector, that would be okay also. Let's stop here. What I'd like for us to do for the remainder of our time is I have our homework quiz here posted into the content library. Just a bunch of vector calculations. There's nothing super duper difficult about it. If you remember how to do your vector operation, should be no problem there. So if you guys want to take out your tablet, fire up your content library, copy that over into your own notebook, do it in your own notebook, and then export as a PDF and drop it into the Dropbox on PowerSchool. That would be good. Again, if you need more space in between things, like if you copy this in, you can press enter in between and make more space if you need it. Some of you guys write big. That's okay. Yeah, I mean, the numbers are straightforward. There's no fractions. They're not inconvenient. You know, like some of the vector operations there, like 2-seconders, you know, like the addition of two vectors, like give me a break, guys. Like you can do that in your head, right? So they shouldn't be, they're not all too bad. You guys can handle it. Yes, sir.
I'm still having like issues when something is already presented to me. IT said they'll fix it soon, but I can't get it. Like sometimes it comes in.
That's weird. Yeah, let's see what's going to be the easiest way to do that.
Sorry about that.
It's okay. Come on. My computer is so slow that I want to just throw it through the window.
I feel that.
This thing can be stopped.